Hello, this is Dr. Leslie Ann Asmus, and in this recording session, we're going to turn our attention to the topic of estimation. Fundamentally, we have a sample that we've drawn. We use a sample statistic as an estimator for giving us some information about the true population statistic of interest. And so I'm going to basically introduce you to one of the areas of this whole of estimation in general, that being the sample statistic of a sample mean being used as an estimator for your population mean. In your textbook, you'll find a number of other focus areas, such as using your sample variance as an estimator for your population variance, using your if you were to draw two samples and look at the two sample means and using those to estimate your population, two different population means, and the difference between those. So let's go ahead and get started just on, this is kicking off, it's giving you a first brush. Here it is. Estimation, types of estimates and the methods of estimation. I'm going to give you a brief glance on that. In the area of a binomial distribution, you might be estimating, these are some additional estimations you might make from samples. You might infer the true proportion, probability of success for your full population based on what you find in your sample proportion. Might be the difference between two proportions, two populations. You're inferring that the proportion might be the same. The probability of success might be the same for a new process as it was the old process. And so you might draw two different samples and see the difference between those sample means, or rather proportions, as estimates for the true proportions in your population. Estimation for a normal distribution. You could use your sample mean as an estimate for your true population mean. So forth like this. So you see a number of these different ones. We're going to focus in this session on the sample mean as an estimate for the population mean. So what we say, and this is what we've talked about before. A statistic is a function of only the values of a random sample, x1 through xn. Those are your sample values. And in general, you have a number of different statistics that we've looked at. And this sample mean is, of course, one of them. You add up the values of the sample observations, and you divide that by n, the size of your sample. This is a little bit of a flavor of concerns that, you can certainly go through a lot of mathematics and proofs of this. But a statistic is said to be unbiased estimator of the parameter, theta, if the mean of that statistic, the expected value of that statistic, turns out to be equal to the true population value, theta, that you were trying to estimate. So another way, if we consider all possible unbiased estimators of some parameter, theta, the one with the very smallest variance is called the most efficient estimator. So you might have different, we look at the sample mean, being sum up all the values, divide by n. Somebody else might say, well, here's another statistic that would be a good estimator for a population mean. Add up all the values and divide by n minus 1. So those would be two statistics that you might both be trying to come up with a good estimator, a good estimate for your true population mean. And so you could mathematically derive and find, okay, which one actually which one has the smallest variance? Which one would have the smallest, such two estimators that have the expected value work out to be theta, and now you want the one that's got the smallest variance to it. We're not going to go through a lot of those mathematical proofs or anything, but just the concept of it. You're looking for unbiased estimators in general. Now, types of estimates. A function of the values of a random sample that yields a single value. A point. This could be a point estimate. So I draw a sample from a population, and let's say my population is the whole of the Dallas-Fort Worth area. and I look at that population, and my interest is the average salaries in that area. So do I want to go to every single home in the Dallas-Fort Worth area and ask what's the salary, household salary, let's make it household salary, and record that, and then come up with the true population mean salary? Not likely people are going to go through that distant effort. So instead, you can draw a sample subset and say, okay, this sample mean, this average of this, say, 100 households that you ask, take the average of the values found. Okay, is this a good estimate for your true population? Well, it may or may not be. A one-off sample, 100 people. You grab them, or you don't grab them, but you go to their households and you ask or you call them, or whatever it is. Maybe you look at tax returns or something like that, and you say, what's your salary? You mark it down, you take your sample mean. And if I were to say, okay, that sample mean is an estimate for the population mean, that one value, that is a point estimate. Different then, you take that sample mean, and then you actually create an interval, two endpoints, a number smaller and a number larger than that sample mean. And then we look at the question of what can one assert with specified confidence that the interval contains the true population mean, the true parameter being estimated, the true value for it. So that's what interval estimates get us into, and creating something called confidence intervals. Types of estimates and methods of estimates. So if we use a sample mean, sorry, these next two slides are pretty wordy, so I'll just read through them. But it really does get at the heart of what this is about. So if we use a sample mean to estimate the mean of a population, a sample proportion to estimate the probability of success on an individual trial, or a sample variance to estimate the variance of a population, we are in each of these cases using a point estimate of the parameter in question. These estimates are called point estimates since they are single numbers or single points being used respectively to estimate mu, the population mean, theta, on the previous slides, the true population proportion or probability of success, and the variance, sigma squared. Since we can hardly expect the point estimates based on samples to hit the parameters as they are supposed to estimate exactly on the nose, it is often desirable to give an interval rather than a single number. We can then assert with certain probability or degree of confidence that such an interval contains the parameter, be it the population mean or the population variance, whatever it is you're estimating, it is intended to estimate. So for instance, when estimating the average IQ of all college students in the United States, we might arrive at a point estimate of 117. And that might be you've drawn a sample of 10,000 students or 50,000 students and found out what their IQs are and say, okay, this is an estimate for the IQ for all the students across all universities in the United States. One estimate. So average 117. Sample average. Do you project that? And say that's the population. Or we might arrive at an interval estimate to the effect that the interval from 113 to 121 contains the true average IQ of all students, college students in the United States. So this is kind of a picture of it. You could draw sample 1. Notice on the vertical axis, what you see there, imagine taking a sample, or out of all those college students across the United States, today you go out and you gather your information for sample number 1. You see that the mean, that sample mean, that first black dot, I don't know, maybe that's 110. And then what you're going to create is, and what you see is the line going on either side of that, that's your interval, okay? And then tomorrow we draw another sample of different college students, and we determine the sample mean, the sample IQ, or the IQ average of that particular sample. We draw another interval around that sample mean, and third sample, and fourth sample, and fifth sample, and sixth sample, and so forth like this. And if you looked at, so here's all these different confidence intervals, all these different intervals around each one of those samples.